In this video, we'll discuss some iterative approaches for solving linear systems of equations. After studying this video, you should be able to explain how the Jacobi and Gauss-Seidel iteration schemes work to solve linear systems. Also, you should understand how an iterative approach can avoid some of the round-off error problems inherent to Gauss elimination. You should be able to predict convergence behavior in certain cases and implement an iterative approach to linear systems in MATLAB. So let's start by looking at this example system of equations. And we can set up an iteration scheme as follows. We can take the first equation and solve that for x1. So we get x1 is equal to 7 plus x2 minus x3 over 4. And solve the second equation for x2. So the first one's for x1. We'll solve the second equation for x2 and write x2 is equal to negative 21 minus 4x1 minus x3 divided by negative 8, and solve the third equation for x3. So we get x3 is equal to 15 plus 2x1 minus x2 all over 5. And the basic idea here is start with initial guesses . We'll start with initial guesses for x1, x2, and x3. Use those to calculate new guesses using these three equations. And then keep iterating that, doing it over and over again until we have convergence. Similar to what we did for roots problems. So let's just formalize this algorithm for any system of equations. So again, here's for a system of 3 equations. We call this the Jacobi iteration algorithm. And we start with initial guesses, and then we will use those initial guesses in the right-hand side here to get our new guesses. And we'll keep track of which iteration we're on with the jth iteration. And just keep going, doing this calculation over and over again. And each time we do the calculation, we'll calculate an approximate relative error for each element. And we'll keep going until all of these EA values satisfy the stopping criterion epsilon s. And it's really that simple. So that is the Jacobi iteration algorithm, is basically to keep solving for new x values until they stop changing, basically. So let's look at a slight improvement to that algorithm called Gauss-Seidel. And the Gauss-Seidel iteration algorithm is a little more popular because it converges faster. And what we do is we assume we have a converging solution, and so we can assume our guesses are improving, and we can make use of the most recent information for each guess. So as we calculate this first equation to get our new guess for x1, what we'll do is take that result and plug that in before we calculate x2. So x2 will use the new guess for x1 along with the old guess for x3. And then we take those results again, take x1 and our new result for x2, and use both of those results to calculate our new guess for x3. And so the convergence is generally faster because we're using our best, most recent guess all of the time. So we already have a value for x1 for our new x1 when we're going to calculate x2, so we might as well use it right there. And that's the simple modification that Gauss-Seidel uses to generally get faster convergence. So before we look at this a little further, let's talk a little bit about round-off error. So recall talking about Gauss elimination that we had all of those repeated in additions and subtractions that could accumulate round-off error and potentially cause a problem. Well, with Gauss-Seidel, notice we are replacing the value each time. So since we're replacing the values of x each time, similar to our roots problems algorithms, we have very little round-off error concern. So that's a good thing. So then the key is, well, does it converge? Well, let's take a look at some examples. So here's that model problem, and looking at the values of x, so x1, x2, and x3 are shown in blue, green, and red, and looking at what those values are doing with the iteration count. And so we see in the solution to the model problem that really by about the fourth iteration here, we've converged to our final solution of x1 equals 2, x3 equals 3, and x2 equals 4. And the rest of this is just meeting that tolerance, epsilon s. So it converges relatively quickly. How does this operation count compare to Gauss elimination? Well, it's roughly the same as the substitution algorithm, recall. So it's going to be approximately n squared operations per iteration. So as long as the iteration count, as long as those iteration counts are less than the number of operations, this is potentially more efficient. And again, for this 3x3 system, it's less efficient because we have 11 iterations on a 3x3 system, so it's more than 3 cubed. It's actually 3 squared times 11. But say we had a 20x20 system, and if it was able to converge in 10, 11 iterations, we'd be in better shape. And again, that's something that you can't really know in advance how fast it's going to converge, so you can do it with trial and error. The main thing that the Gauss-Seidel iteration is addressing, though, is the round-off error concern. So let's look at another case. Here I'm just going to take that same model problem and I've rearranged it. The equations now are in a different order. And what we see is now, again, starting with initial guess of x is equal to 0, the solution, basically, we would say this, blows up. It's a diverging solution, and you can see that that happens right away. This second figure zooms in on the first few iterations, and you see even by the second iteration things are starting to diverge. And we're not getting to those final solutions. So here we see that the Gauss-Seidel method can diverge. And let's look at what's different. So if we come back to the first example, we see that the largest elements are on the diagonal in that coefficient matrix. And it turns out that that's the key. In this case, the largest elements are not on the diagonal. The 2 is less than the 5, and the 4 is greater than the 1 here. So because the largest elements aren't on the diagonal, the solution tends to blow up. And you can see that if you look back here, it's at the iteration algorithm, the diagonal elements are here in the denominator. So if those, as long as those diagonal elements are in the denominator, that makes sure that these numbers are only going to be changing by the minimum amount with each time as we converge on the solution. So this is a property of the matrix where these three numbers are the greatest on the diagonal that we call diagonal dominance. And this is a little bit different than what we talked about with partial pivoting. Recall for partial pivoting with Gauss elimination, we wanted the magnitude, basically the pivot elements, to have the greatest absolute value in each column. And actually for diagonal dominance, we are going to be looking more at the rows. And what the diagonal dominance theorem means is that if the absolute value on the diagonal is greater than, and here's the key, greater than the sum of the absolute values of the other elements in the row. That's what that summation notation is telling us. And so looking back at our model problem, we have to have the 4 is greater than the absolute value of -1 plus the absolute value of 1. And the 8 is greater than the absolute value of 4 plus the absolute value of 1. So that's our criterion for diagonal dominance. And a key about diagonal dominance is that it guarantees convergence, but it's not necessary. So the solution may still diverge even if the system is not diagonally dominant. So let's look at how we can implement this in MATLAB. There's no built-in function for Gauss-Seidel, so we need to write our own iteration scheme. And so we can do that, and we'll start by rearranging our earlier algorithm in matrix form. So all I've done is rewritten this algorithm here, this expression here, in matrix form as b minus some b divided by those diagonal elements minus some matrix. So let's look at what that matrix is. Just rewriting that gives us a matrix that looks like this, and we're going to call this matrix C. This is just for coefficients for the algorithm implementation. And here's the b divided by the diagonal elements, b's over a's. And we will call that D, call that vector D. And then we can write this in a compact form, x equals D minus Cx. Then for Jacobi, we can just do this over and over again and do it as a matrix operation. For Gauss-Seidel, we have to make sure that we redo this iteration, but we need to go row by row, so we're always using the most current information as is specified by the Gauss-Seidel iteration algorithm. So let's look at an M file to implement Gauss-Seidel. So here's an M file using a lot of the same basic form that we used for our root solving algorithms earlier. I haven't included a lot of the help comments, but one thing noted here is that it does have to be a square matrix, so I've included an error message for that. And here we are going to build that coefficient matrix C and the vector D. And to build the vector D, I'm using the built-in function diag. This basically pulls the diagonal elements out of A and gives us a column vector of diagonal elements that we then use to create that D vector that we needed. Recall the iteration scheme is x is equal to D minus C times x. So then what we'll do is go through and build that coefficient matrix. So what I've done here is going row by row through n rows. We're going to go each row at a time. So the ith row, elements 1 through n, so all elements in that ith row, I'm going to just divide them by that diagonal element. So recall that's what's happening here, is each element in the ith row is being divided by the diagonal element. But then what we also have to do is zero out this diagonal, because these are all 0 elements here in that coefficient matrix. So I'll do that. That's the next step. We're just going to zero out the diagonal. And now we've built the C matrix and the D vector that we need for our iteration scheme, and it's time to execute the iteration. So pre-allocating our error vector, and then we'll go through the iteration scheme, storing the old value of x, and now again going row by row for, since this is a Gauss-Seidel iteration, so that on the second iteration, this value of x, on the second iteration of this for loop, this will always be the most current value, even though we haven't completed the entire iteration of the algorithm for the matrix. We've just finished the first row. Then using the built-in all function to make sure that nothing is equal to 0, and calculating our approximate relative error values, and then using just the maximum approximate relative error value as a check to compare to the stopping criterion and stop the algorithm when we meet that. And this Gauss-Seidel M file is available for download in the video folder. And that concludes this video.